This is a vector review. It's going to go through finding the magnitude of a vector, finding the angle of a vector relative to the x-axis, vector addition, vector subtraction, vector multiplication by a scalar, scalar product or dot product, and vector product or cross product.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude.
Let's jump right in with a first example. Vector A is 2i minus 3j. So let's label a coordinate system. I'm going to take positive x to the right, positive y to be up. In a 3D coordinate system, this would have positive z out of the page. For vector A, we normally would write that the x component next to the I hat, the y component next to the j hat, and the z component next to a k hat if we had a z component. Comparing our given vector 2i minus 3j with the given form, we see that ax is equal to plus 2 and ay is equal to minus 3, az equal to 0. Let's draw vector A before we do anything else. So my ax is plus 2, that's 2 units to the right. My ay is negative 3, so that's 3 units down. Then my vector A, since ax is to the right and ay is down, vector A will be to the right by 2 units and down by 3 units. If you think about it in terms of a tip to tail drawing, it goes from the tail of ax to the tip of ay when you draw ay tip to tail with ax. Okay, the first thing we're asked for, what is the magnitude of vector A? You might notice that vector A is the hypotenuse of a right-angled triangle where ax and ay are the legs. That means we can use Pythagorean theorem. The magnitude of vector A, or the length of vector A, is going to be ax squared plus ay squared, take the square root. So that's the square root of 2 squared plus minus 3 squared. 4 plus 9, so we've got the root of 13. You can leave it like that, or you can find that the root of 13 is about 3.61. We're also asked for the angle between vector A and the x-axis. Let's notice here that that angle is below the positive x-axis. It's in the fourth quadrant. We can use trigonometry to find that angle. We know all three, ax, ay, and the magnitude of A, so we can use any of those. We can use sine, cosine, or tangent. It is customary to use tangent. So tan theta is opposite over adjacent. Here the opposite is the y component and the adjacent is the x component. One thing to make notice of here, when you do tan theta opposite over adjacent, you always use the magnitude of those values. And that's mostly just because your calculator is a little bit funny. When we look at our picture, we know that the angle is in the fourth quadrant. Sometimes your calculator doesn't know what quadrant it's in, and sometimes it's going to give you an answer back in a funny quadrant. If you look at your picture so that you identify the quadrant and you put in all positive values, then you'll always get the right answer. This means then that theta is the inverse tan of ay over ax, the magnitudes of those guys. So that's the inverse tan of the magnitude of ay is 3, the magnitude of ax is 2. Put that through the calculator, we get 56.3 degrees, not quite finished. So the magnitude of vector A is 3.61 units, and the angle of vector A is 56.3 degrees below the x-axis. You can write it like this, or you could write negative 56.3 degrees. Both would be acceptable. Okay, let's do another example, this one having a z component. So in our coordinate system, positive x is to the right, positive y is up, positive z is out of the page. When we look at our vector B, bx is minus 4 units, so it's 4 to the left. There is no j hat, that means by is 0, and bz, the part that comes out of the page towards us, is equal to plus 1. Let's start by trying to draw that vector. I'll sketch in my coordinate system, leaving myself some room to draw. There's x and y, and positive z is out of the page. So my vector b is 4 units in the negative x direction. So that's 4 to the left. And my bz is 1 unit coming out of the page. Trying to do a 3D drawing. I'm not super good at it, but hopefully you're getting the idea. Then my vector b will come from the origin to my tip of my bz arrow. So it's 4 units to the left and 1 unit out of the page towards me. So that's what vector b looks like. Now we can go through the same process we did with part A to find the magnitude and the direction. The magnitude of b is equal to, that's the hypotenuse of a right angle triangle where x and z are the legs. So bx squared plus bz squared equals the square root of minus 4 squared plus 1 squared. That's the square root of 17. You can leave it like that, or you could write that that's equal to 4.12. Okay, here's a good spot for a little side note. If you had all 3 components, then the magnitude of vector b would be bx squared plus by squared plus bz squared. So if you had all 3, you would use all 3. Okie dokie. Now for finding the angle, let's label our angle. So I'll draw my angle theta relative to the negative x-axis. I'm going to use tangent again. Tan theta is opposite over adjacent. So it's the size of bz divided by the size of bx. Let's make sure I get it in the right quadrant. So theta is the inverse tan of the magnitude of bz, that's 1, divided by the magnitude of bx. Magnitude of minus 4 is 4. So it's the inverse tan of 0.25, which is 14.0 degrees. Now when we write down our answer, we'll say that the magnitude of vector b is 4.12 units. The angle of vector b, this one might be a little bit harder to write down because we're used to saying above or below x. So the angle is 14 degrees, and we might say as drawn, or we could say from the negative x-axis towards the z-axis. That would be an accurate description as well. Now, if you didn't like that sort of 3D drawing, you can always rotate your coordinate system.
Right-handed coordinate systems can have any orientation as long as they're all the same, x, y, and z, as long as they're the same relative to each other. So take your right hand and hold it up so that your thumb sticks out, your index finger sticks out, and your middle finger sticks out. Your thumb is x, your index finger is y, and your middle finger is z. So you can have your coordinate system any which way at all. So this is always x, always y, always z. It can point whichever way you want it to, as long as that relative orientation is maintained.
I'm going to redo the problem on the next slide. I won't talk you through it in a video, but I'll draw a new rotated coordinate system that might be a little bit more comfortable to look at and for drawing. Okay, next let's find the sum of our two vectors and the magnitude of the sum. Just before we get started, I'll just put in the little warning light. The magnitude of A plus B would not be equal to the magnitude of A plus the magnitude of B. That's not a general rule, that's true. Okay, let's get started. What is A plus B? So let's say that vector C is vector A plus vector B. That means that the x component of C is the x component of A plus the x component of B. So that would be 2 plus minus 4 to give us minus 2. Then likewise with the y component, AY plus BY. AY is minus 3, by is 0 to give us minus 3. And same deal for the z components. It's az plus bz, which is 0 plus 1 to give us 1. Those are the x, y, and z components of vector c. So then when we write c as a vector, it's the x component minus 2 units plus the y component minus 3 units, and the z component, which is 1 unit. You can write in the 1 or you can just write in k hat. So there's vector c, which is a plus b. If you wanted to draw this, you could certainly give it a try. It would be 2 units to the left, 3 units down, 1 unit out towards you. I find that a little bit hard to draw adequately, so I'm just going to skip the drawing on this one. Okay, for our magnitude of a plus b, that means find the magnitude of vector c. So that's the magnitude of a plus b. To do that, we're going to apply our Pythagorean theorem in the general form when we have all 3 components. So that's going to be cx squared plus cy squared and cz squared. Take the square root. Okay, so negative 2 squared plus negative 3 squared plus 1 squared. Those are all added up. We take the square root. So 4 and 9 is 13 and 1 is 14. So we've got root 14. Or if you prefer in decimal form, 3.74. Okay, there's addition covered. Okay, now in this example, I'm going to call it vector subtraction, but it's not truly a vector subtraction. It's still kind of a vector addition. So we're saying, what is A minus 2B? So vector C is vector A, subtract 2 times vector B. Well, that's exactly the same thing as adding vector B, except you multiply vector B by negative 2 first. It's the same sort of deal. So we're still really doing an addition, but we've multiplied a vector by a scalar, and that scalar is negative 2. The way this works is that the x component of vector C is the x component of A minus 2 times the x component of vector B, or plus minus 2 times the x component, same deal. The x component of A is 2, and we're subtracting 2 times the x component of B, which is negative 4. Okay, 2 times minus 4 is 8. 2 plus 8 is equal to 10. So vector C will be 8 units long in the positive x direction. The y component is AY minus 2 times BY. AY is equal to negative 3. BY is equal to 0. So we get negative 3 for our y component. And for our z component, we have AZ minus 2 times BZ. AZ is 0, minus 2 times 1 gives us minus 2. So those are my components. To write C now as a vector, I've got 10I minus 3J minus 2K. If you're a good hand at drawing, you might draw this 3D. I'm not so hot, so I'm not going to try. Okay, for the magnitude of vector C, or the magnitude of A minus 2B, we'll just have to do the square root of the x component squared plus the y component squared plus the z component squared. So that's going to be the square root of 10 squared, that's 100, plus the square root of minus 3 squared, that brings us up to 109, plus the square root of minus 2 squared, brings us up to 113. So that's the square root of 113, or 10.6. So now we've finished covering finding magnitudes and angles, addition and subtraction, as well as multiplication by a scalar. Next, what if we want to multiply two vectors? Turns out there are 2 ways to do that. The first way is the scalar product, sometimes called the dot product. The scalar product, or the dot product, that's a way of multiplying any 2 vectors that gives a scalar for the result. So the result doesn't have any direction. Some examples you might be familiar with are work, where work is the dot product between force and displacement, or in the integral form, work is the integral of F dot dr. So those are both 2 ways to write down the scalar product. Or you may be familiar with power, which is force dotted with velocity. Work and power are both scalars. They do not have any direction when you find those values. Okay, next let's look at the rule for finding a scalar product or a dot product. So when we find the scalar product or a dot product, it's really important to remember that we do have to write the dot in between the two. And there are two ways to evaluate a scalar product. First, we can say that A dot B, or the scalar product between A and B, is the magnitude of A, and that's what that A stands for there. So A means magnitude of vector A, times the magnitude of vector B, times the cosine of the angle between them. And that part is really important. This theta here, like any angle, it's always an angle between two things. And this angle theta is between vectors A and B. Got to be careful for that in problems. Sometimes you're given an angle and it's not quite the right angle, so your best bet is to draw vector A, draw vector B, and identify that angle between them. So that's one method of evaluating a scalar product or a dot product. The other method is if you know the components. So method one works if you know the magnitudes and the relative angle. The second method works if you know the components. So AX, AY, and AZ, BX, BY, and BZ are all the components of A and B. Okay, so there's our two methods. The method you use really depends on the stuff that you have. So before we get into an example, we'll just put in the one last thing where the scalar product is something new. And that's if we have I dot I, remember I hat is a unit vector, it's a vector of length 1 that points in the x direction. So I hat unit vector, which means vector with length 1, and I hat points in the x direction. J hat is the unit vector that points in the y direction, and k hat is the unit vector that points in the z direction. We've been using that as we go, but here's your formal definition. When we take the scalar product between these unit vectors, I dot I is 1, j dot j is 1, and k dot k is 1. I dot j is 0, j dot k is 0, and I dot k is 0. So something dotted with itself is 1, something dotted with something else is 0. You can see that's true just by using version 1 of how to calculate our scalar product rule. Scalar product, maybe one last note, scalar products are commutative and distributive. And what we mean by commutative is that A dot B equals B dot A. And you'll see distributive as we go through the example on the next slide. So we have two ways of evaluating the scalar product, and the way you choose depends on what you're given. For this example, we know that A is 10 in the x direction, and B is at 5 units at 30 degrees above the horizontal. We'd like to find A dot B. Here we have the magnitudes of the two vectors and the angle between them. Seems like using the first method would be the easiest. So if we take our coordinate system where positive x is to the right, positive y is up, positive z is out of the page, then vector A is 10 units to the right. Here's vector A. We see that the magnitude of A is equal to 10. Vector B is 5 at 30 degrees above the horizontal. Might not be a perfect drawing, but it's kind of okay. 30 degrees. So the magnitude of vector B is equal to 5, and the angle between those two vectors, we've drawn it, and we see clearly that 30 degrees is the angle between the two. Our angle is theta. So now let's apply the first method. A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So we have 10 times 5 times cosine of 30 degrees Put all that through the calculator, you get 43.3. So there's your scalar product using the first method. In this example, we have vectors A and B, the ones we were working with earlier, given in unit vector notation, and we want to find the scalar product A dot B. We could jump right into the equation that was given, but let's work through it and see how the scalar product is distributive. So A dot B is equal to 2i minus 3j dotted with, and that dot is important, 4i plus k. So what we're going to do is multiply out all of these terms. Some people in high school maybe used to call this the FOIL method. So to start, I've got 2a dotted with minus 4, 2i dotted with minus 4i. Okay, next I've got 2i dotted with plus 1k. Okay, next I've got my minus 3j term, so I've got minus 3j dotted with minus 4i, and finally I have minus 3j dotted with positive 1k. All right, when you're writing it out this way, the next thing you do is multiply the numbers and leave the dot products at the end. So 2i dotted with minus 4j is 2 times minus 4, that's minus 8, I dot I. Okay, next, plus 2 times 1 is 2, I dot k, plus minus 3 times minus 4, that's plus 12, j dot I, plus minus 3 times 1 gives us minus 3, j dot k. Now we have to put in what we know about these scalar products. I dot I is 1, I dot k is 0, j dot I is 0, j dot k is 0. Any two things that are perpendicular have a scalar product of 0. Okay, that leaves us with an answer of minus 8. This answer, you'll notice, is a scalar. That means that there's no I or j or k in it. And this is just like the example we had on the previous slide. Now, had you wished, you could have jumped right to the equation that was given for scalar product, which is A dot B equals AX BX plus AY BY plus AZ BZ. And you'd see that you get exactly the same thing that we have above. AX is 2, BX is minus 4, plus AY, that's minus 3 times BY, which is 0, plus AZ, which is 0, times BZ, which is 1, to get minus 8. Same answer either way, but going through the top process hopefully just shows you a little bit more in depth about how to use the scalar product. One kind of nifty thing about scalar product is you can use it to find angles between vectors that's hard to do geometrically. So let's say we have our vectors A and B and we want to find the angle between those two guys. So I think the first thing I'll do is let's just see how that's hard to do geometrically. So there's X, there's Y, there's Z. We've already drawn these vectors once, but let's just do it again. So vector A is 2 units in the x direction, negative 3 in the y. So vector A is down here. Vector B is negative 4 in the x direction and plus 1 in the z. So vector B was over here. So B is to the left and out of the page. A is to the right and down. And the question says, what is the angle between those two guys? Okay, that is not an unsolvable problem, but to me, geometrically, that could take an amount of work. Let's see if we could use the scalar product instead. So we know that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between these two guys. Well, we actually know a lot of this. We know that A dot B is equal to minus 8. We found that on the previous slide. We know that the magnitude of vector A was 3.61 or root 13. And the magnitude of vector B, that was the square root of 17 or 4.12. We can just go straight ahead and solve for theta. So why don't we do that? Cosine theta is equal to A dot B divided by the magnitude of A times the magnitude of B. So minus 8. And the negative sign is important here because that's what's going to give you an angle bigger than 90 or smaller than 90. Divided by A, 3.61. Remember that means the magnitude of A times the magnitude of B, 4.12. That gives us 123 degrees. So the angle between vectors A and B is 123 degrees. Maybe if you really like geometry, you might try and figure that out geometrically. So we've already covered one method to multiply vectors. That's the scalar product. The second method of multiplying vectors is the vector product or the cross product. So a vector product or a cross product, that's a method of multiplying two vectors that gives a vector for the result. So when you do the notation for this guy, there's a times symbol or an x between the two vectors. That's really important. That indicates that it's a vector product and not a scalar product. The scalar product had the dot. That's why we call it a cross product, because there's a cross between them. Examples of a vector product would be calculating a magnetic field. So B, and we're going to cover that in this course in Physics 1051. B is mu naught over 4 pi times Q times V cross R hat over R squared. That gives the magnetic field made by a moving charge. And another example where we use a cross product is calculating a magnetic force, which is QV cross B. So that's the magnetic force on a moving charge. So those are some examples we'll end up covering. So to calculate a vector cross product, you can do that in a couple of ways. The magnitude of a vector cross product is the magnitude of vector A times the magnitude of vector B times the sine of the angle between them. So that will give the magnitude. And then you find the direction, generally using the right-hand rule. You can also find a cross product using the equation A cross B. If you use the equation A cross B, you have to know what I cross I, J cross J, K cross K, I cross J, J cross I, and all those. You have to know what all those are equal to. So here's a table of all those results. You can sum it up in a little shorthand notation. If you write I, J, and K in a triangle, and you point one to the other, if you go the right way around the circle, you get a positive answer. So for example, I cross J is K. Plus K, but if you go the wrong way, for example, J cross K, you get negative I. And then something crossed with itself is 0. Okay. So a couple of interesting things to point out. Any two vectors that are parallel or anti-parallel, that's when you get I cross I or J cross J, that's equal to 0. And if you have perpendicular vectors, that's when your cross product is a maximum. So A cross B will be equal to the magnitude of A times the magnitude of B. We said that scalar products were commutative. Vector products are anti-commutative. So it matters which order you do your cross product in. A dot B is equal to B dot A. A cross B is not equal to B cross A, and in fact, it's equal to negative B cross A. You'll probably have to prove that result in one of your math classes. And like scalar product, a vector product is distributive, and we'll go through that in an example. Let's take our two familiar vectors and let's find the cross product between A and B now. So vector C is equal to A cross B. On a previous slide, there was a long general equation for calculating the cross product. And let's more or less go through that now, but we'll apply the distributive property and see how you come up with that. So we've got 2I minus 3j crossed with minus 4I plus k. Again, that cross symbol is really important because it differentiates it from the scalar product. Now we'll go through the distributive property. We've got 2i crossed with negative 4i. Then we have 2i crossed with k. Okay, now we have the minus 3j terms. So we've got minus 3j crossed with minus 4i. And then we've got minus 3j crossed with plus k. Just like we did when we did the scalar product version of this problem, we'll take all of our scalars out front and we'll leave the vector bits at the end. So 2i crossed with minus 4i is minus 8i cross I. Okay, next we have 2i cross k, so that's 2i cross k. Why don't I even put brackets around that so it just pops out a bit more. Plus, now I've got minus 3 times minus 4, that's 12j cross I. Plus, minus 3 times 1 is minus 3j cross k. Here's where we have to remember what all those various cross products are. So I'm going to write down that triangle because I find that helps me remember. I cross I, something crossed with itself, that's 0. I cross k, we're going the wrong way around that circle. So I cross k is equal to minus j. J cross I, we're going the wrong way around the circle. J cross I is going to give us minus k. And then we have j cross k is the correct way around the circle, and our result is plus I. So let's write down that result. We've got minus 8 times 0, that's 0. 2 times minus j is minus 2j. 12 times minus k is minus 12k, and then minus 3 times I. Now, you certainly may leave your answer like this. It is more customary, though, to write them in order I, j, k. Minus 3i, minus 2j, minus 12k. Okay, so there's the result of A cross B. Something interesting to note here, and certainly you can prove this, vector C is perpendicular to vector A, and vector C is also perpendicular to vector B. So when you take a cross product, the result is perpendicular to both of the constituent vectors. For one last example now, let's say that vector A is 10i hat and vector B is 5 at 30 degrees above the horizontal. Let's find A cross B. Let's find this one using magnitude and direction. So vector A is 10 units, points to the right. Vector B is 5 units, points at 30 degrees above vector A. And let's say that our coordinate system is x, y, and z. So positive z points out of the page. If we want to find A cross B using magnitude and direction, the magnitude of vector C is the magnitude of vector A times the magnitude of vector B times sine theta, where theta is the angle between A and B. So let's put in what we know. The magnitude of vector A is 10 units long. Magnitude of vector B is 5 units long. The angle between those two is 30 degrees. So when we put that through the calculator, we get 25. This gives us the magnitude of the vector. And of course, we also need to find, sorry if you heard that, that was my dog just having a big shake right next to me. So for a vector, we also have to find direction. Let's use the right-hand rule to find direction.
To find the direction of A cross B using the right-hand rule, take your thumb and you point it in the direction of A, that's to the right. Take your index finger, point it in the direction of B, so that's up and to the right. Stick out your middle finger, that's the direction of C, so that should be out of the page or towards you.
To indicate out of the page or towards you, you would draw that on your diagram as a little dot inside of a circle. So that's vector C out of the page like this. So the notation is out of the page is a dot, into the page is an X, That comes from an arrow notation. If you imagine an arrow or a dart with some flights on the back, if it's coming towards you, you see the tip of the arrow, that's the dot. If it's going away from you, you see the flights, that's the x's. And then in terms of our unit vector notation, out of the page is the z direction. So we would write vector c is 25 units. We would either write the words out of the page or use k hat to show the z direction, positive z.